Hi everyone, welcome to chapter 13. I have an introductory video that if you have not watched already, then you should go watch it, assuming I remember to put it up. And we're going to dive into the first section of chapter 13. So I'll just make a couple comments about chapter 13, a little more technical than my intro video. We saw a little bit of vector valued functions in unit 14 towards the end there, and it might have looked strange, but it wasn't totally beyond comprehension how to handle them, what little we did with them. And that was smoky. Hard to avoid that when I'm filming at home. Okay, so we are going to be looking at the definition of a vector valued function, and then we have to learn how to define it, learn how to take limits, understand its continuity, learn to take derivatives, and ultimately learn to take integrals. And now that everyone in the class has done their integrals section, for those who are dual enrolled in both this class and in AP Calculus BC, we can get on with anything that involves integrals. So from here on out in the class, integrals will be introduced and used on a regular basis. At first, in a way that's very familiar in this section, we'll introduce that. And then as we move through the rest of this chapter and into the last chapter, 15, we'll be doing almost nothing but integrals. All right, let's keep moving. All right, so I want a generic picture of a vector valued function right here. The function is the blue curve in space, and the r vector is a position vector that is determined by these three components, f of t, g of t, and h of t. So each of these are components, but they're not constants. Notice they are component functions. And so you saw a little bit of this in the last chapter, and now here's a good picture of what's going on. T is our independent variable, in most cases time, and it can be given a specific interval of real numbers to operate on, assuming something that we're measuring is moving along a pathway for a fixed amount of time that we're interested in. Of course, it could be moving on forever, but we may not be interested in what it's doing after a certain time. So what I want you to realize is that for every point on this curve, which is, of course, an infinite number of points, there is a position vector which we get from a certain t value plugged into our component functions. And so there's lots and lots and lots of vectors that we could draw. I'm not going to, so if I wanted to focus on this point, that would be an r vector, and that's what we define it as r. That's our function letter. The letter r is what we use for our position function. So the position that a particle has along a pathway, in our case in space. This could also be in the plane, but we are going to use space most of the time. And so there are any number of vectors leading to any and every point on this curve from the origin, and every one of them are of some value t is the name of it. All right, so let's just look at this. I want you to think about what the graph of this function looks like. If I did not include the t component, so cover up t for a moment, if we had cosine of t for the I component and sine of t for the j component, can you think of what this curve would be? Well, if it's just ij, that means it's in the plane, and want you to think of anything that this might bring to mind that we have a more familiar equation for. If you have to pause to think about it before you look, then please do. All right. Now, if you did pause to think about it, I hope that you thought about the fact that when you square our two component functions and add them together, the I and j components, that we know that this has a constant value of 1. And I'm curious to know if you're thinking about what this function comes from. It goes back to the unit circle. Okay. And so what we've got here without this component is a unit circle in the xy plane. If we put one or of these trig functions under k and then deleted another one, it would be a unit circle in a different plane. So if it was cosine ti plus sine tk, it would be in the xz plane. And if it was sine tj plus cosine tk, it would be in the yz plane. So this is just a unit circle without the third component. However, When we put in a third component, I'm just going to put plain t. And I want to know if you can figure out what that turns this unit circle into. A unit circle in the xy plane. And as time ticks by, this component in the z direction gets bigger little by little. So what do you think is happening to our circle? Is it a closed circle any longer? Is it a pathway in 3 dimensions now? So this would suggest we're moving off the xy plane. As long as t is positive, we would be moving up. And as long as t is negative, we would be moving down, but in a circular pathway. So the official word for this function is a helix. All right, see the blue pathway is traveling along the outside of a cylinder of radius 1. They noted that the circle in the xy plane is x squared plus y squared equals 1. And they've noted points along. If t is 0, we're at the point 1, 0, 0. If t is pi over 2, we're over here, and we travel around. There's t equals pi, and there's t equals 2 pi. And so we are traveling along the surface of this cylinder in a shape called a helix. Okay. So you've heard this word before in biology class, a double helix, that is the form that a strand of DNA takes. So I want you to look at these three, just one at a time really. This is the one we just examined. We noticed it had a radius of 1. And if we do 0.3t, notice how it coils around more frequently in the same amount of space that it does here. By the way, just so you know, these all have the same scale, these 3 coordinate octants, or sets of octants, the coordinate space, basically. And so what makes it curl around faster? Well, 0.3t, so it goes around, it doesn't go up as high for every turn, so there's more turns in the same amount of vertical space. Here we just have plain t, but this affects the frequency, just like it would if you were graphing y equals cosine of 5t. It affects the frequency of the curve. It turns faster. For every second that ticks by, it's going through a larger angle. So each of these are ways to put more turns in your helix. And so the k component makes the curve increase. As long as the k component is positive, it's going to go upward. If the k component were negative, it would go downward. Now, since most of you have a Mac, or all of you in the class this year have a Mac, I want to play with the Mac grapher here. So, first of all, how you enter equations for curves like this, you would go down here to the plus sign and you would hit a new equation from a template, and you would choose Cartesian surfaces. We have not yet learned cylindrical or spherical graphing, so we're just still doing XYZ graphing, and you would choose this. And we're only doing functions in one independent variable t, so I'm going to delete u, although you could do functions in u. And I've chosen for these curves to go up to 20 just to see more of the spiral, okay? You would put the x, y, and z, or I, j, and k components in these 3 little boxes, just as I have over here, and then we can see what different changes do to different curves. Okay, don't need that one. So I've got this one, I've got cosine and sine, I've got a z value of 0, so I just have my unit circle. We can see from this that the scale, every hash mark is a distance of 2. We could zoom in if we wanted it to look a little bit bigger. I have no idea why it made the no, that's the x-axis thicker. I know that's the x because to its right is y and z is up according to the right-hand rule. So if you want it to stop rotating, you click on the screen. If you want it to move, you get it started and it will keep moving. All right. So I'm looking at the first octant. Here's our unit circle, and z is 0. So this is just lying in the xy plane, but I could do as they did in the previous equation and make this t. It doesn't go around very much. If I made it 0.3t, goes around more often and so forth, like we saw in the previous slide. So we could really play with this. I want you to think about the continuity. Is there any limit to the domains of sine and cosine? No. To 0.3t? No. So this is a continuous curve in both directions forever. We've only graphed t equals 0 to 20. Okay. Now, we saw this one on the other page. All right, let's uncheck that. Oh, I can't leave that. I'm going to put 0 back there. So getting rid of that and going to this one, we have a spiral. we saw that it makes it go around more frequently, like cosine is turning through a larger angle when you put the coefficient in front of t, but it's basically the same concept. It's still a unit circle with a radius of 1. So we increase the frequency either by multiplying t by smaller numbers, or in the z component, or by multiplying t by coefficients larger than 1 inside the trig functions. So how do we change the radius, basically? Well, if you're looking at the other equation, changing the radius here, and I'll zoom out. So, you zoom out far enough and we can look at it this way and we see the radius. It looks like it's getting bigger each time, but it's not really. I think that is just how this draws it, how it renders it. So there are definitely some limitations to drawing 3D on a computer, because this 4 here would be the radius. A multiplier in front of the trig functions would change the radius of the curve. So if we graphed these on the same curve, and I change this back to t, you could see, and if you really want to make these thicker and easier to see, you can increase the thickness. I also change the color so you can see the difference. So you can see the difference between the radius of 1 and the radius of 4. And it really should be lined up so that this looks like a circle. The helix does not open up wider as it goes. So that's a flaw in this software's graphing. The software, however, is excellent software by any means. The ease of entering equations into it compared to online graphing systems like Desmos, which is fabulous, but is not really set up for 3D graphing officially. It's a huge headache to do 3D graphs on Desmos at this point, and they say they're working toward making it easier, and I look forward to that day because of some of the flaws in existing programs. However, Grapher is probably, for Apple, is probably one of the best ones out there. I actually had a copy of this program but long before Apple Grapher existed. They bought it from a company called Pacific Tech, and they do a great job. You can buy this for other computers that are not Mac computers from Pacific Tech directly off their website. So it's not super cheap. It's $60 or $35 for students or something like that, or was a few years ago. So if you like this grapher, it is pretty good. And if you don't have an Apple in the future and you want this grapher, then Pacific Tech, T-E-C-H, spelled traditionally, is the way to go. Okay, well, this is how you can check your hunches and see if equations in vector valued functions are what you'd expect them to be. And they put them in little they look like matrices. A matrix with a single column or a single row is just a vector. So these are in vector form to enter them into here, but we're still going to use IJK form for vector value functions. Here's my other kitty. Okay, she has to walk in front of me, apparently. There you go. Okay, keep moving. All right, so let's go back here. We'll just take one more peek. What if we mess with more trig functions? Now, trig functions are periodic functions, so they're going to have repeated behavior over and over again. And so we just want to see a little bit what happens to them when you start messing with stuff. Tigger, have a seat. No, not on my notes, though. Yeah, come over here. Come over here. All right. So it's hard to tell what cat you're recording. All right, so over here we've got a repeated pattern. The first curve under A, so we've got interesting shape. We've got sine 3t times cosine t. This would be one that would be fun to plug in and just play with the numbers. So we've got sine of 3t, which got multiplied by our basic helix, and it causes it to repeat this extra bit of loop. Instead of just going around, so it starts at the origin, has a little loop there, and rises up to a loop here. So it's interesting. If you trace it, you get a better feel for the curve. It's just kind of a little secret. And so I can pretty much relate to that curve a little bit better for having traced it. It's just going to repeat that shape forever. And so multiplying the trig components by sine of 3t puts extra little loops in there. Well, this one, putting sine of 2t here, makes it look like a really steep Pringle outline. What you want to see, you want to go to the grapher and see if sine of 2t changes things. So let's use this one. Let's just do sine of 2t for now, okay? I'm going to turn that one off. And every time you change it, the line goes back to a really thin line. I'll just zoom in. Okay, so there's our really tall Pringles shape from the picture on the other page. And so what happens if I just make it sine of t? What do you think is going to happen to it when it's just sine of t? Well, let's find out. All right. So let me orient it. Okay, so that's looking at it from above. From above, it looks like a circle. From the side, so it is a circle. Is it? Wait a minute, does it have the same radius everywhere you look? Yeah, it's at a 45-degree angle off of the XY plane, lying in, that's kind of interesting. So it is just a circle if we don't do 2t. And if we do 2t, we get the Pringle. What about 3t? So it makes it have an extra bump. So it has 3 peaks on the top and 3 valleys on the bottom when you put a 3. Is there a pattern going on here? 4. Okay, well, we see what happens. And this is how you play with it. So you would get the repeated hills and valleys more frequent around the circle. Okay, so apparently when it's just sine of t, you get 1 up and 1 down, but they don't look like a Pringle anymore. This looks like a circle in a plane that is making a 45-degree angle with the XY plane. So that's kind of interesting and fun to play with and to develop a sense of. This one's really crazy. They've done 4 plus. That takes it off the center. So in the I direction, we're 4 off the origin down the X direction. In the Y direction, we've gone 4 this way. So the center of the curve is hovering over the 0.44. And then we've done 20 up and down zigzags. This looks like a spiral, like a spring that's been, or a slinky that you've taken and curved and closed it up on itself. And then this cosine t, that's actually a little bit interesting to see what that would do. So I'm going to let you play with that one in the grapher and just understand the periodic nature of these functions, and they can become predictable. It would be interesting to play with this number 20 in these and see how that changes it. All right. So the definition of a limit. So a new kind of function means we have to go through all the definitions. So the definition of a limit, here's our, of course, very formal definition of a limit that we reviewed earlier in the semester. And so the limit of r of t as t approaches t naught just means that you take that same limit of each individual component function. So look at example 2 down here. If we want to take the limit of r of t as t approaches pi over 4, first we ask, is pi over 4 in the domain of each of these functions? And it is. So we're simply going to, we could write this out, and I hesitate to because this tablet is so hard to write on, but take the limit as t goes to pi over 4 of cosine of t, and that'll be our I component, and so forth. Okay, I won't make you watch me do that, but since pi over 4 is in the domain of each of the functions here, then we just do direct substitution. So, silence my phone, sorry. So if I plug in pi over 4 into each of these functions, I'm going to get cosine of pi over 4, I, sine of pi over 4, j, and pi over 4, k. So we're going to have, I'll just put it right here, root 2 over 2i plus root 2 over 2j plus pi over 4k. That would be the limit of our function as it approaches pi over 4. So if we go back and peek at this function, when we first saw a picture of it, pi over 4 is going to be somewhere in this direction. So we would go root 2 over 2 this way, which is what, 0.7? And then root 2 over 2 in the y direction, and then up. So I'm thinking that our substituting pi over 4 gives us the limit right there. There's the point that the curve is approaching as t approaches pi over 4. All right. Always good to do a visual component of whatever we do algebraically here. Okay, so looking at the continuity of a vector valued function, Basically, it's continuous if all of the component functions are continuous. So if it is continuous at the point at which the limit is being evaluated, then it's simple substitution to figure out the limit as t approaches that value. And so it's continuous if it is continuous over its interval domain, okay? So example 3 here is not really a question. They're just demonstrating continuity and discontinuity. So all of the curves we looked at in space in the previous pages were continuous because we had every value of the real number system that was able to be plugged into it, all right? And continuous and periodic, by the way, every single one of them, since we were using trig functions. Now, we take this function, and cosine t is continuous and sine t is continuous over all real numbers, but the greatest integer function is a piecewise function, essentially, and it is not continuous. So what in the world is that going to look like? We're only going to have integer values of our k components. So we're going to have these skips where I'll have part of a circle and it'll hop up and part of another circle and it'll hop up. So let's go and see what that's like. So I am going to put the greatest integer function in here. And you can go to your palette, show equation palette, and I'm going to choose the greatest integer function here. So it's really called the floor function, and put t in there and hit enter. So we're going to get these little bits, okay? This is just where, so everything that would have been curving up to continue this up here is now projected downward onto the xy plane, and this is projected down onto all the points that would be rising from here to here, and this is turning. Instead of reaching upward, then it's been flattened down like somebody cut it and flattened every layer down like it's a staircase, and this is the front edge of every stair going around in a spiral circle. So that's kind of interesting, and we could make this line a little thicker, make it a little easier to see, and you can see, when I do like this, you can see. And again, it's making it look like the radius is increasing when it's not, but it would just be the front edge of every stair going around a spiral staircase. Like it's just basically been chopped and flattened at each integer plane of z. So that's kind of interesting. All right, so how do we take a derivative of a vector valued function? There's excellent derivation of this process using our limit definition of a derivative. And so the definition of the derivative at the value t of a vector valued function r of t is simply found by finding the derivative of f with respect to t. So f is the I component. Take the derivative of g, dg dt for the j component, dh dt for the k component, and that's how you take the derivative. So r prime of t. So we're looking at the fact that the derivative of a vector valued function is also a vector valued function. Okay, say bye-bye, ticker. She's pretty persistent. She'll probably jump back up. All right, so when is a function like this differentiable? Well, continuity and differentiability go hand in hand, and we would certainly, if we have a nice smooth curve with no cusps, that's the word for points, like this on a curve, with no cusps, and no, this is not a discontinuity, it just looks like it was a smooth curve and somebody broke it. Not technically a cusp, since these are the concavity of both curves on either side of the point are in the same direction. But this would also be a non-differentiable point. So a curve is smooth, okay? So for a smooth curve, and there she is, we would be differentiable everywhere that the component functions were differentiable. And then piecewise smooth would be like this picture where pieces of it are smooth, and then there would be a non-differentiable point, and between two non-differentiable points would be a nice smooth curve that would be differentiable. So we would simply have individual points and individual values of t where the function that's defined piecewise is not differentiable, okay? So, by the way, since these pathways are always supposed to be mimicking motion, we consider the derivative, the direction that it's positive is the direction of motion. And so when a curve is smooth, we never have a zero derivative, okay? We don't really consider it going in reverse direction just because it's negative and it never stops. So we really deal with positive values of our dr dt rather, when we take derivatives of functions, a position function, or any of its derivatives. We would always consider them moving in the direction, or positive and moving in the direction of motion, in the positive t direction. Okay, and that's practical because if t is time, t doesn't go backwards and it isn't negative. So that's a practical limitation, but it's acceptable because that's how the world is. Okay, so particle motion is a topic you studied in single variable calculus, and it boils down to this. When we have a position vector, and in single variable calculus we tended to call it S, but S is reserved for arc length in this class, so we're going to call our position function R. Notice these are bolded, and in handwriting you wouldn't be able to bold it, you would just put a bar over it, or let me do some better handwriting. You would write it like this in handwriting to indicate that it's a vector valued function. If you leave this bar off, I'm not going to assume it's a vector valued function, and it might actually be wrong when it comes to answering something. And just want to train you right. Some people will say a professor that insists to use symbols right is being mean or being too harsh on the students, but frankly, if you don't put the bar over that, then I don't know it's a vector valued function. Even if it has ijk, it's a wrong symbol and it means something else, and it would be wrong. So please, when you talk about vectors in handwriting, would you put the bar over it? Whether it's simply a vector like v without the parameter or the independent variable beside it, or when it's actually got the independent variable, that's fine. But if it's a vector valued function, put the proper symbol. All right. So velocity is always the rate of change of position. So dr dt is our velocity vector. Okay, and that these are, keep in mind, these are all vector valued functions. All right, and if we take the magnitude of velocity, we get speed. Okay, so I want you to remember that when they ask for velocity and speed and acceleration. All right, and finally acceleration, if it exists, if this derivative dv dt exists, gives us our acceleration function, which you can also call a of t. But it's a vector function, so please put your vector bar over it. Perhaps you've talked about the next derivative, the third derivative in single variable calculus, that the rate of change of acceleration is going to be a function called jerk. I don't know if you've ever heard of that. I don't even know if it's a part of the AP curriculum anymore. But if you think about it, have you ever ridden in a car with a manual transmission and somebody can't smoothly change gears, so the acceleration keeps being interrupted by gear changes and it makes you move a little forward in your seat, it jerks you around. So it makes sense that the rate of change of acceleration is called jerk. It's kind of interesting. We don't do much with that in applications, but it is a nice fact to know. And so sometimes we see F triple prime in a meme t-shirt or an internet meme that says don't be a F triple prime, which means don't be a jerk. So now you'll get those jokes. All right. So notice all the notation we use here. V is dr dt, speed is the magnitude of v, a is dv dt, or the second derivative of r with respect to t. And then if we divide vector v, the velocity vector, by its own length, we get the direction of motion at time t. Okay, so all of those are little formulas that they'll put into application questions. So let's look at this one. This is still theoretical with no application behind it, but let's see what we're doing. A picture of what it is to figure out. The picture actually depicts velocity. So find the velocity, speed, and acceleration of a particle whose motion in space is given by this position vector, and then sketch it. So I cheated and I went ahead and gave you the sketch because I don't think that necessarily we have enough experience to look at 5 cosine squared of t and be able to sketch that right now. Okay, you probably haven't played with it enough to be able to do that. But what we need first is velocity. Okay, so I need to take the derivative of each of these functions. The first derivative of 2 cosine t is negative 2 sine t in the I direction. Remember, I use little hats over unit vectors. All right. Derivative of 2 sine t is going to be 2 cosine t in the j direction. And then the derivative of 5 cosine squared t, remember this is going to need the chain rule. It's going to be 5 cosine of t, and, oh, bring the 2 down, so not 5, but 10. Okay, 5 times 2. Second power comes down to first power, and then the derivative of cosine t is negative sine t, so I will go back and change the sign here to negative, and that will be in the k direction. So there's our velocity vector, and we can go ahead and do the velocity at 7 pi fourths. Now notice the picture here. They've pointed out where t is 7 pi fourths, and they've drawn the tangent vector to the curve right there. So when we plug in 7 pi fourths here, so 7 pi fourths is here, which is going to be root 2 over 2 for cosine and negative root 2 over 2 for sine. So negative 2 times negative root 2 over 2. So negative times negative is positive, 2's cancel. That's going to be root 2i. And then cosine is going to be positive root 2 over 2 times 2, which is plus root 2j. And then, so we're going to have minus 10 times root 2 over 2 times negative root 2 over 2. That's minus. So negative times negative is positive. We're going to have 10 fourths, which is 5 halves. And root 2 times root 2 is 2. So 5 halves times 2 is 5 plus 5k. Okay, so there is the value, the velocity, the speed at, or excuse me, that's the velocity vector. And then they didn't ask for the speed. Yeah, they didn't ask for the speed of this particular one, but they want the speed, which would be the absolute value of this vector. And I'm going to peek at my notes and see. No, I didn't remember to do that. Okay, so the magnitude of v is going to be the square root of 4 sine squared and 4 cosine squared. So I'm going to go ahead and do this. Okay, and then 100 cosine squared times sine squared. If I factored a 4 out of this, then I wouldn't just end that. I would make this plus 25 cosine squared sine squared, and that 4 would come out. And we'd have 2 square roots. This is 1 plus 25 cosines, sine squared, cosine squared. Either order is fine. So this is going to be our speed at time t, our magnitude. And if we had to plug in a particular value, we would be able to do it to this formula to find the speed at a given point in time. It did not ask us to do that, so I'm going to move on to acceleration. So I have to take the derivative of the velocity vector valued function, so a of t. All right, so the derivative of negative 2 sine t is going to be negative 2 cosine t in the I direction. And then the derivative of 2 cosine t is negative 2 sine t in the j direction. And then here we're going to have, oh, the product rule. Okay, so I'm going to do negative 10 out front. And we're going to have uv prime plus vu prime. However you've memorized this is fine. So cosine times cosine. So u is cosine, v prime is cosine, so cosine squared of t, plus vu prime, which is sine times the derivative of cosine, which is sine, so plus sine squared of t, which is a happy result because this is just 1. So our acceleration function is here without rewriting it. So this just equals 1. So it's negative 10 times 1, and that's in the k direction, that last component. And there you go. That's very similar to what you did in single variable calculus, and it feels like single variable calculus because each of those component functions was just a function of t. So even though we're working in space, it's easier because the component functions currently are single variable functions. They could be multivariable functions. That would still work too, and you know how to take partial derivatives, so you're good there. All right, so all of the rules of differentiation that apply to single variable functions apply to these, to vector valued functions as well. Derivative of a constant is 0 and so forth. Notable differences being two different product rules. So u prime v plus uv prime, same thing but with dot products for two functions being dotted together that are vector functions. Of course, they have to be vectors if they're being dotted together or taking the cross product, either way, and then the appropriate product is inserted in the formula you're familiar with. Chain rule also applies, which you saw me do with cosine squared. So this is not anything particularly new or different. All right, wonderful proofs on pages 756 and 757, and some of the exercises ask you for proofs. All right, my kitty cat is trying to cross the street again here. All right, we're almost done, Tigger. Hang on just a little while longer. All right, so now our surface in space is a sphere, and I want you to notice that coming from the origin, position vectors would be radii, which we know would be all the same length just because of the nature of a sphere. And so we have a curve along that surface and a point P identified on that surface, which is at the tip of our r vector. And then when we draw dr dt, that vector, we know that a radius drawn to a sphere is going to be perpendicular to tangent lines to the sphere. So this vector is tangent to the sphere. So we know geometrically that this is going to be a right angle, because in geometry class long ago you learned that the radius of a circle makes a right angle with a tangent to the circle. And the same is true in 3 dimensions. So we know geometrically that it's true. By the way, this is, there's no actual proof of this other than visual proofs. It's more of an axiom or a postulate than a theorem, okay? But now we're going to do this with calculus. So if r is a differentiable vector function of t of constant length, which is what we've got here, then r dotted with dr dt is going to be 0. So we see in the picture it's true. The question is, can we prove it? All right. Turns out to be rather easy to prove, strangely enough. And so what we're going to do is we're going to come up with, all right, so we're going to come up with, if we dot, okay, r prime, okay, r of t dotted with r of t. So a vector valued function dotted with itself, okay? We're going to give it, and this is strange, so let me check my book. I wrote a constant value. It is going to be a constant value, and I want to check what I'm thinking here. Okay, so we don't know. So a vector dotted with itself, what we do know is that a vector dotted with itself, not a magnitude, but a vector dotted with itself is going to be the square, sorry about that. It's back in our notes back here on the previous page. Is going to be the length, that's what it is. It's going to be the length of the vector. So, sorry about that. So it's going to be some length, okay, and I can call it squared if I want to, and I'm trying to see. Yeah, it's the length of r. I don't know why they put c squared, okay? It doesn't really matter in the end. But we could say, take the derivative of both sides, okay? So the derivative of, and I'm going to write it d dt of r of t dotted with r of t. Sorry, lost my momentum there. Okay, and the derivative of a constant is 0. So it didn't really matter that it was squared. I'm kind of curious why they did that. And so we're going to apply the product rule for the dot product here. And we're going to have r prime of t times r of t. So that would be uv prime plus vu prime next. So we're going to have r of t, and these are all vector valued functions, times r prime of t, which is 2 r of t r prime of t. Okay, and that still equals 0 from up here. And we divide both sides by 2, and that goes away. So r of t, and this would be a dot product, okay, dotted with r prime of t equals 0, according to our little short proof here. So that's not too hard to prove. It was a little confusing why they bothered to put c squared up here. And then exercise 27 in the book would have you prove it backwards, okay? So if r is differentiable, vector function of t, show that the product is 0 for all t. So if the product is 0 for all t, then the absolute value of, or the magnitude of r is constant. And rather than make you watch each step of the way here, let me get my arrow. All right, so they're saying if r dotted with r prime is 0, then prove that this is a constant number. So prove that it's a sphere that the curve is lying on. So starting with the derivative of r dot r, okay, and that's going to be product rule here. So r dotted with r prime plus r prime dotted with r. So that's just applying the dot product rule. And same step as we did up here. That's these are identical terms, so it's just 2r dotted with dr dt. And then that's going to be 2 times what we know to be 0 here. We know this is 0 from the if part. So 2 times 0 equals 0. All right. And that means r dotted with r, the derivative of r dotted with r is 0, which means r dot r is a constant value. And the magnitude of r, square root of r dot r, is a constant number. So that's pretty simple, but it does say something different than what we did before when we do it backwards. All right, thank you for listening.